according to widely held philosophical fake news, the developments in mathematics that ensued from the revolution that we discussed last week finally freed us of these ancient antinomies. In particular, in the Principles of Mathematics, Bertrand Russell claimed that by strictly banishing all infinitesimals has finally shown that we live in an unchanging world, and that the arrow at each moment of its flight is truly at rest. Now, I would like to take it slowly here. And last weekend, when you described this revolution, sometimes called the arithmetization of mathematics, you mentioned in passing that when by the time the dust of this revolution settled, infinitesimals had gone out of the window. And this is what Russell is referring to there. Infinitesimals have a very ancient and interesting history. They went out of the window several times, and they resurrected like a mathematical phoenix. And could you reconstruct in outline the history of infinitesimals, what they are, what conceptual role they played, why they were invented, and how they ended up out of the window?
Yeah. Okay. So I think it's fair to say that most philosophers nowadays wouldn't take Zeno's paradoxes very seriously. And one of the reasons is the revolution in mathematics in the 19th century, which showed us a certain understanding of infinitesimals, or better, how to get rid of infinitesimals. To a certain extent, I think that's true. I think to a certain extent, the developments in mathematics do solve at least 3 of Zeno's paradoxes. I'm not persuaded that they solve the arrow, but we can come back to that. Let me do what you ask and talk about infinitesimals. So, the theory of infinitesimals, at least the sort of major beginning of the theory of infinitesimals, is in the 17th century with the work of Leibniz and Newton. And Leibniz and Newton were concerned with motion, change, rates of change, and they needed some mathematics to handle this phenomenon. And what they did was introduce the notion of an infinitesimal to give some mathematical apparatus to talk about what happens when things change. And an infinitesimal is a quantity that is smaller than anything you it's as close to 0 as you can possibly be whilst not being 0. Now, if you think of just real numbers, you know, there's nothing that's there's no real number that's closest to 0, because any real number has half that real number, which is close to 0. But the infinitesimals were things which were smaller than any real number, but yet not 0. So these are rather strange quantities. Berkeley dubbed them ghosts of departed quantities. Okay. So how did this strange mathematical machinery work? Okay, let's take a simple example. Suppose that you've got something that's moving, and it might not be moving uniformly. It might be sort of speeding up, slowing down, and so on. But take some instant of that motion. What is its velocity at that point? So we want to know its speed, what its speed is at a point. Now, speed is distance over time. So So if you got a stretch of time and you take the distance that the thing travels in that time and divide it by the time, you've got a speed, but it's the kind of the average speed over that time. It's not the speed at any one instant. And of course, the actual speed at an instant can be changing over this period of time, so it gives you an average, right? We want more than average. We want to know what the speed is at a particular time. So what do? Well, here was the thought of Leibniz and Newton. Speed is distance over time, but it doesn't do any good to take a kind of a real interval of time, because then the speed might be changing over that time. So what you do is you choose an infinitesimal amount of time. So that's something just long enough to have a duration, but so small that there's no change of velocity possible in that instant. Okay, so then what you do is you consider this infinitesimal distance. So you've got this time, you want to know the velocity at that time, you choose an infinitesimal distance that the thing goes from that time and divide by this infinitesimal time that it takes to move, and you get, wow, the instantaneous velocity. Okay. So that's how infinitesimals were supposed to work conceptually. Okay, so these infinitesimals are rather strange quantities, that was clear. But once you start to look at the mathematics, at how it works, there are certainly problems that have become apparent. Now, let me emphasize that the results of applying the mathematics were kind of spectacular. They really worked. Using his infinitesimal calculus, Newton was able to make predictions about celestial and terrestrial motion, which were just a quantum leap, so to speak, better than anything that had been achieved before. So the mathematics was really very successful. But when you look at how the mathematics was working to do this, it has an obvious feature. Now, I've noticed that these infinitesimals are rather strange, and this strangeness is reflected in the mathematics. So when you look at a computation of velocity, for example, you've got to take the distance that this thing moves in this infinitesimal time, and you've got to divide it by the infinitesimal time it takes. That's the way you compute velocity, right? Velocity is distance over time. So this infinitesimal time, it cannot be zero, because in mathematics, dividing by zero makes absolutely no sense. So an infinitesimal cannot be zero. Okay. The trouble is that when you do this division of this infinitesimal distance by this infinitesimal time, you get a number. That's okay. And typically the number is going to be an ordinary real number plus some infinitesimal junk. So you might discover that the thing moves at the rate of 2 meters per second plus some infinitesimal. All right. Trouble is, you don't really want the infinitesimal in your answer, because you want an answer like 2 meters a second or whatever. So what you have to do is then say, well, okay, we can ignore the infinitesimal. So let's regard it as zero. So you've got this thing that's moving. We don't want any infinitesimals in the answer. So therefore we have to assume that the infinitesimal is actually zero. Okay, so at one point in the computation, you have to assume that the infinitesimals are zero, and at one point, you have to assume they're not. Well, it's just a reflection of the fact that you're conceptualizing these infinitesimals as something which are non-zero, But they're so close to zero that you can ignore them when you want to. Okay. So the infinitesimals appear to have contradictory properties. This was not a trade secret. Everybody knew this. Berkeley, when he wrote about this in Demo 2, where he coined this phrase, the ghosts of departed quantities, points out that they seem to have contradictory properties, and it was a sort of challenge to Newton to get his act into order. Well, you know, the mathematicians didn't get their act into order. They operated with the infinitesimal calculus very successfully for the next 200 years, 150, 200 years. So it certainly appears that the mathematics in this period was working on a theory of numbers, infinitesimals, which seemed to have contradictory properties. And everyone knew this. They didn't worry too much about this. Actually, I mean, a lot of people will tell you that contradictions can't be true because scientists are always troubled when they find contradictions in their theory. They want to get rid of them. Well, okay, yeah, they do sometimes, but here's an example where they didn't. So make of that what you want, but that's a side remark. Anyway, so that's where infinitesimals first appeared in the history of mathematics in seriousness, and what happened for the next 100, 150 years.